Okay, let's look at an introduction to titrations. Now, we're going to balance the neutralization reaction. You've got sulfuric acid combining with sodium hydroxide, and you are making water and sodium sulfate. So since you've got, I'm going to rewrite water as HOH here, and I'm going to balance the hydrogen and hydroxide separately because you have a hydrogen at H2SO4 and a hydroxide and sodium hydroxide. So since you've got two sodiums on the right, I'm going to put a 2 in front of NaOH to balance the sodium, which gives me 2 hydroxides. So put a 2 here to balance the hydroxide, and then that gives you 2 hydrogen, and it looks like we are balanced. It's 1, 2, 2, 1. Number 2 says write a balanced equation for the reaction between aluminum hydroxide, so that's Al plus 3, OH minus 1, cross the numbers in the charges. There's your aluminum hydroxide. Hydrobromic acid is a binary acid, so hydrogen and bromine, so it's HBr. And then you're forming aluminum bromide and water. So that's Al plus 3, Br minus 1, cross the charges, and you get Al, Br3, and water, which I'm going to write as HOH because I have a hydrogen and a hydroxide in 2 different compounds, and it's easier for you to balance the hydrogen and the hydroxide separately. So if I have 3 hydroxides on the left, I'm going to put a 3 in front of HOH to balance the hydroxide, which gives me 3 hydrogen. So I'm going to put a here in front of HBr to balance it. Then that 3 also goes to the bromine. I already have 3 bromine, so this is my balanced equation, 1, 3, 1, 3. For number 3, it says complete and balance the following equation. This is ammonium hydroxide combining with sulfuric acid, which I'm not going to write as sulfuric acid. I'm going to write it as hydrogen sulfate. And then what I'm going to do is I'm going to take the ammonium and the hydrogen, and they're going to switch places. And you're going to get hydrogen hydroxide and ammonium sulfate. And then since I have hydrogen hydroxide, which is just water, I'm going to write that as HOH here because of the hydrogen and the hydroxide in 2 separate compounds. And then I've got ammonium sulfate, which is NH4 plus 1 and SO4 minus 2. You're going to cross those charges. The NH4 goes in parentheses with the 2 on the outside, and then the SO4. Now, if I have 2 NH4s, we're going to put a 2 here to balance the NH4. And then that 2 also goes to the hydroxide, so we're going to put a 2 here. And then you have 2 hydrogen, which you already have here. So 2, 1, 2, 1 would be the balanced equation. Now, in number 4, it says, write the formulas for the acid and base that will react to give the salt, potassium carbonate, and water. I'm going to write water as HOH. Now, if you want to predict the acid and the base that produced this salt and water, you know that a base contains a hydroxide. So that means that there's a cation that has to go with the base. The cation is going to come from the salt. Since this salt is potassium carbonate, you look at the salt and you take the cation, potassium, and you combine it with hydroxide. Potassium is a +1, hydroxide is a -1, so that means your base is potassium hydroxide. An acid begins with hydrogen and it has some anion attached. This anion comes from the salt. It's the carbonate. So this would be hydrogen carbonate. So this is H plus 1, CO3 minus 2, cross the charges, you get H2CO3 for your acid. Okay? Now, let's move on and let's talk about titrations. Here. So a titration is a method that's used to determine the concentration of an unknown solution by reacting it with another substance of known concentration. The most common types of titrations are acid-base neutralization reactions and redox oxidation reactions. And in this section, we're going to focus on acid-base titrations. And when you have a neutralization reaction, you know that an acid combines with a base to produce a salt and water. And if we take a look at the next page, we're going to look at some sample problems, and there are a wide variety of sample problems pertaining to titration calculations, and I'm going to show you some of them. Let me see if I can make this a little bit bigger just to make it easier. There, I think that helps. And let's take a look at number 1. So number 1 says a student titrated 25 milliliters of HCl with 15.62 milliliters of 0.3 molar NaOH. Calculate the hydrochloric acid concentration. Okay, you have to write a balanced equation. So this is NaOH plus HCl. You're going to make sodium chloride and water. And it's already balanced as it is. And you've got 0.3 molar NaOH and 15.62 milliliters NaOH and 25 milliliters of HCl, and we want to know the HCl concentration. Sorry, there's like a big glare over that, what I just did. That is terrible. Okay, so let me write that over here. Okay, so that's what I do every time I'm doing a titration problem. Your balanced equation, write the numbers and the units underneath the appropriate substance because it'll help you figure out where you should begin. Now, you know that if you have molarity and liters of something, you can multiply them together to get moles, because if you cover up moles in the molarity triangle, molarity times liters is moles. So step number 1 is going to be molarity times liters will give you moles of NaOH. You always want to ask yourself, how could I possibly get moles? So we're going to take our 0.30 molarity times 0.01562 liters, and that's going to give you 0.0046 moles of NaOH. Now, you've got to convert your NaOH to HCl using the coefficients. So step number 2 is going to be moles of NaOH to moles of HCl using the coefficients. So we have a 1 coefficient in front of HCl and a 1 coefficient in front of NaOH, which is why you get 0.0046 moles of HCl as well. Then if you want molarity, molarity is moles over liters. So step number 3 is going to be moles divided by liters equals molarity of HCl. So take this divided by 0.025 liters of HCl, and this will give you 0.187 molarity HCl. Okay? Okay, now let's take a look at another problem. Let's go ahead and do problem number 2. We have NaOH combining with H2SO4. So I'm just going to go ahead and write out the balanced equation, and then I'll put the numbers in the appropriate place. I've got 10 mils of NaOH, and we're calculating its concentration. I have 24.25 mils of H2SO4 at 0.20 molarity. So you always want to ask yourself, how could I solve for moles? Molarity times liters of H2SO4 is going to give me moles. So molarity times liters will give me moles of H2SO4. So 0.20 molarity times 0.02425 liters will give me 0.00485 moles of H2SO4. Then in step number 2, you're going to convert moles of H2SO4 to moles of NaOH using the coefficients. So there's a coefficient of 1 in front of H2SO4 and a coefficient of 2 in front of NaOH. And then in step 3, you're going to take your moles divided by liters to give you molarity of NaOH. Just make sure that you're dividing by the liters of NaOH here. So this is going to be your 0.01 liters of NaOH, and this will be 0.97 molarity. Okay? Now, number 3 is exactly the same as what we just did. Number 4 is slightly different. So I'm going to take a look at number 4. So we have a reaction in number 4 between H2C2O4 and NaOH. Okay, here's your balanced equation. We have 0.5 molar of the acid, and we want to know what volume, so that means I'm looking for liters. And then you have a 0.12 molar NaOH, and you have 10 milliliters of it. So step number 1 is going to be, how could I possibly get moles? Well, molarity times liters of NaOH will give you moles of NaOH. So you're going to take 0.12 times 0.01 liters, which will be 0.0012 moles of NaOH. Now we're going to do a mole ratio in step number 2. Moles of NaOH to moles of H2C2O4 using the coefficients from the balanced equation. So this is 1 mole of H2C2O4 over 2 moles of NaOH. And this will give you 6 times 10 to the negative 4th moles of the acid. Okay? Now, you know from the molarity triangle that if you're solving for liters, you cover it up and it says to take moles over molarity. So step number 3, moles divided by molarity equals the liters of your acid. So you need to take the moles of the acid and divide it by this 0.5 molarity. And that will give you 0.0012 liters of the acid. Okay? Now, let's talk about some practical aspects of titrations. So in a titration, there are 2 solutions. Let me make this a little bit smaller. And the solution whose concentration is known is the standardized solution, and the other solution is the unknown concentration. And we have to use precise measuring tools when we're doing this because our answer needs to be really precise. So we have to make sure that we're recording our data to the proper number of significant figures. It's super important. So the special glassware that we use helps us get really accurate information. And it's important to know the different names of the glassware that you're using. So the first is a burette. And the burette contains the standardized solution. That means the solution of known concentration. So let me pull this here. So you're going to put your burette in a ring stand, and you would use this for your titration. This burette would have your known concentration or your standardized solution in it. Now, the numbering system on the burette, sometimes it's numbered 0 at the top to a different number at the bottom, like 50 or 25 mils. Sometimes it starts at 0 at the bottom and it goes up to 50 or 25. Do not worry about how the numbering system goes. Just record whatever value you're at initially and the final volume. So to measure the initial volume before the titration and the volume final after the titration is important. And you usually record them in a table, and you subtract those two volumes to get the volume of standardized solution that was added into a flask. So for instance, if you're using an Erlenmeyer flask, which we usually are, we would add that directly into it, and typically you are recording your volumes 2 places past the decimal or the hundredth place because the precision or the division size here is 0.1 milliliters, okay? Now, let's come down here and talk about a pipette. A pipette is used to measure and deliver a very precise volume of a solution of unknown concentration to the Erlenmeyer flask. And pipettes come in a number of different sizes. For instance, I have a pipette here. This is a 10 mil pipette, and they can be 1 mil, they can be 5 mil, they can be 25 mil. And sometimes they look a little bit different than this. Sometimes you're going to see it and it's going to have sort of like a bulb in the middle of it. And that's still considered a pipette. And we either use a pipette bulb to suck up the solution into the pipette, or we use a device like this, which is super handy to suck it up, and then we dispense it into our Erlenmeyer flask. We never suck up the liquid by mouth. Now, if you take a look here, an Erlenmeyer flask is what contains the measured volume of a solution of unknown concentration, and then we add a few drops of an indicator at the beginning of the titration. So we draw up whatever volume of our unknown solution with our pipette, and then we're going to dispense this into the Erlenmeyer flask, and then we add a few drops of indicator. We typically use phenolphthalein, and then the indicator is going to change color when the reaction between the moles of acid and the moles of base is complete, okay? If you take a look at the next page here, there are a couple of terms that you should be familiar with. The first term is equivalence point. The equivalence point happens when the moles of hydrogen ions equal the moles of hydroxide ions. And when the indicator changes color, you hit the end point. And that's when you record the final burette reading, okay? Let's take a look here at the quick check. is a pipette different from a burette? So a pipette delivers a specific volume of solution. And the solution is suctioned up into the pipette. Whereas a burette is used to gradually add a volume. And it has a valve. Number 2, what solution goes into the burette? That's usually the standardized solution, which is the solution of known concentration. Number 3, which piece of glassware is the indicator added to? The Erlenmeyer flask. Number 4, what is equivalent at the equivalence point? Moles of hydrogen ions and moles of hydroxide ions.